Hi there, thanks for joining us. This is Space Nuts Q&A, where we answer audience questions. And on this episode, we're going to be talking about the relationship between dark matter and the cosmic web. We'll also look at an issue that's been raised about the synchronization of communication between Earth and long-distance spacecraft. How do they do that? Because they're moving at a rate of knots at great distances away from us. So how do we talk to them? There's also questions about whether or not there's more than one asteroid belt, and can we build a space wheel? We'll tackle all that today on Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Here he is again, Professor Fred Watson. Hello, Fred.
Hi, Andrew. How are you?
I'm as good as the last time you saw me.
Good.
I'm even wearing the same shirt, strangely enough.
It's extraordinary, isn't it? So am I. What a
coincidence. Yeah, amazing. Are you ready to tackle some questions?
Why not?
All right, let's get down to it. Now, our first question, or questions, come from the same source, and it's Ben. And he's got a couple of interesting ideas. He says, hi there, Andrew and Fred, long-time listener but first-time questioner from Chicago, though originally from Australia, just in the form of a text, as I'm one of the lucky sods who's gotten COVID twice in 2 months. And can't talk. I'm sure some people can appreciate that. Just have two questions, not related. And, of course, one is going to be about dark matter. Fred mentioned in an episode that matter and dark matter don't interact. And one way of seeing that was some galaxies have moved over time, but the blob of dark matter doesn't move with it, to paraphrase. But if that's the case, my question is, how did dark matter form the cosmic web pattern of the universe in the first place if it doesn't move? Since galaxies are theorized to be held together using dark matter, wouldn't them moving off the dark matter blob mean they would start to fly apart? That's his first question. We'll get to the second one after we've solved that riddle, Fred.
So the interaction, there is an interaction, which is via gravity, the least understood of all the fundamental forces. And that's why, if you've got a universe, a baby universe that's got this web of dark matter, because that dark matter has gravitational interaction, then it will pull the normal matter in. So you do get, the galaxies strung out along the cosmic web, as we find today when we observe galaxy surveys and things of that sort. The point I was making about the lack of interaction of other kinds, in other words, that, they don't bounce off one another, was a couple of examples where we know that clusters of galaxies, which are the biggest sort of objects in the universe, they've collided, and the gas and stars in those galaxies have sort of ground to a halt in the pileup. So what you end up with is a big blob of galaxy debris, except it's not debris, it's much the same as it was before they interacted, but they're gravitationally probably pulling one another apart and things like that. So you got two galaxy clusters, they collide, and you get a smash up there, which you can identify as being two different galaxy clusters colliding. But the dark matter from each of those, because each of those clusters would have had its own dark matter halo, the dark matter just carries on. It doesn't interact either apparently with itself or with the debris, the normal matter. So what you've got is a scenario where you've got a new cluster of galaxies that's been formed from the two colliding clusters, and on either side of it is a blob of dark matter, which is the dark matter from the two original clusters that's just carried on going because it doesn't impact the normal matter. It does gravitationally, so it'll tend to have a gravitational influence on it, but the dark matter basically just just carries on.
It's very confusing, Fred. I can understand why we get so many questions about it, because it just doesn't seem to make sense.
No. The only thing that makes sense is that the particles of dark matter and normal matter don't sort of bounce off one another, but they do have a gravitational effect on each other. That's maybe the way to put it.
Okay, that makes it sound a little bit more simple, I hope. Now, Ben's second question, which is for spacecraft. Communicating with them takes obviously longer and longer the further they are away. With all the planets moving all the time along with gravitational differences, the further or even closer to other orbital bodies, how do we keep the spacecraft synced to Earth perfectly? Would we, for spacecraft very far away, have to pinpoint or point telescopes further ahead of where they will be if it takes hours for the signal, or if it's close to a body like the Parker Solar Probe, would that not mess with the signals with delays or possibly the signal bending somehow? I'm sure these are taken into account, but I just wonder how people plan for it. I know telescopes account for this with redshift, but I wasn't sure how two-way communication with satellite probes works. That's a really interesting question, because we take for granted that we can still communicate with Voyager, and it's way beyond anything else that we've set out so far.
That's right. It's 22 light hours away at the moment, I think, if I remember right.
Yeah.
So it is a good question, but it can all be compensated for. And in fact, Ben mentions the bending of signals, and there's a classic case of, I think it was the Cassini-spacecraft when it was on its way to Saturn. This is in the early 2000s. It was at one point behind the sun to us, but we could still see the signals because they were being bent by the gravitational effect of the sun, just like light is. It's general relativity says that gravity will alter the direction of a beam of light or a beam of radiation. And that was one of the ways, actually, the Cassini observations of signals coming from the spacecraft being on the backside of the sun, but still being able to see the signals, was one of the confirmations of gravitational deflection of light. So once again, underpinning relativity's absolutely fundamental place in our understanding of the universe. And yes, if you had a spacecraft that was moving across our line of sight, and occasionally they are doing, because they're, if you've got gravitational slingshot maneuvers, that might well put the spacecraft on a trajectory that's going across our line of sight. You do need to aim your radio telescope ahead of it. You've got to take it into account, and people do that, and it's completely routine. So because we understand what the orbits are doing, it's basically a routine, maneuver or maneuver of telescope operators. Probably the person to talk to about this is Glenn Nagel, who looks after the Tidbinbilla tracking station, one of NASA's deep space tracking network, which is not far from Canberra. I might talk to him about it next time I see him.
Yeah, why not? So Ben was pretty spot on with his analysis. That's right. Ben goes on to say, thank you for answering this rambling and for the wonderful podcast. He said, I also worked for the ABC in Ultimo for a while. That's in Sydney. So maybe we crossed paths, Andrew, and never knew it. I was in the dark corner of the newsroom. Ben, I never got to the newsroom much. I think I actually only entered the newsroom once in my life, and I could feel the tension the moment I walked in. I know they talk about the atmosphere of places creating certain awareness amongst humans. I've never felt more intimidated than the day I walked into the ABC radio newsroom. I could feel how, I don't know, how deep the place was. as an observer. And that's where they make all the news and current affairs programs for ABC New South Wales. And I don't envy you being there. I couldn't have worked in that environment. It was just too much for me. I liked my little regional radio job out in the sticks, much more relaxed. Thank you, Ben. Great to hear from you, and hope all is well in Chicago. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Let's get some audio questions sorted out, Fred. And one of our regular sender-inners is Sandy from, I'm going to say Melbourne. I said that last time and I was wrong, or was it Brisbane? I don't know. Sandy somewhere.
Hi, Fred and Andrew. It's Sandy from Melbourne again. My question today is about the asteroid belts between Mars and Jupiter. As I understand, that's where the primary asteroid belts are. Now, is there any other asteroid belts that's past the orbit of Jupiter? So I'm referring to perhaps out towards Neptune, that sort of, or Uranus sort of distance. I'm assuming the answer is no. And if the answer is no, how come they've sort of massed together between Jupiter and Mars and not further out? Thank you.
Thanks, Sandy. If you've got asteroids around Uranus, I think you should see a doctor, but they're more likely to be hemorrhoids. Sorry, I couldn't help it. Yeah. And look, I like the question because my first thought is, well, hang on, the asteroid belt, yes, know all about that. Is there another one out there? And I just thought, well, there's the Kuiper-belt, but it's not the same, is it? Or is it the same?
You're right, Andrew. It's true that there are other asteroid belts, and they're quite different in character. So Sandy's right that the main asteroid belt is the one, and the most highly populated is the one that lies between the orbits of Mars and Jupiter. And that's been known about since the early 19th century. The first one of those series was discovered on the 1st of January 1801, and that set the path for, the understanding that there is a belt of small objects between Mars and Jupiter. We used to call them minor planets, in fact, when my MSc thesis is called The Determination of Minor Planet Orbits. There you go.
Mm.
That's what we now call the main asteroid belt. Actually, Sandy's right, because he's talked about it as being multiple belts, and in a way there are different families within those asteroid belts, within that main asteroid belt, if I can put it that way. We talked about some of those in the last episode of Space Nuts. Now, as regards other asteroid belts, yes, there are. And as you said, Andrew, the Kuiper-belt is what really comes to mind, and that's just one of a number of different groups of icy asteroids which are beyond the orbit of Neptune, which is why they're called trans-Neptunian objects. One of the bigger ones is called Pluto, but it is just one of the bigger ones. And there are different families within that group of trans-Neptunian objects. There are objects called classical Kuiper-belt objects. There are objects called resonant objects, where they have a resonance with the orbit of Neptune. And then the most distant ones are called scattered disk objects. So these are three different groups of objects which are in that outer asteroid belt. They have a different formation, we think, from the inner asteroid belt, because they're mostly icy, those objects, as we know Pluto is. And that means that what we're seeing is a family of objects that really are the remnants of the cloud of dust and gas from which the solar system formed. It's at the outer extremities, objects that have never been warmed up by the sun, the star that formed in the middle. Whereas the asteroid belt is principally rocky objects, and we think it's just a sort of cloud of debris that's been shepherded into that particular orbit between Mars and Jupiter by the huge gravitational pull of Jupiter. Jupiter's gravitational influence is enormous on other planets and the minor planets, and we think that's what it is. There's a region between Mars and Jupiter where debris is collected, and probably it's still primordial debris. It's the rocky material from which the planets were made. But it was never able to form a planet because there's this giant right next to it, as gravity is kind of swishing it around a lot.
Yeah.
So, yes, logical reasons why we understand these different sorts of belts.
What about the Oort-cloud?
Yeah.
Would that be an asteroid belt of some kind?
I meant to mention the Oort-cloud. Thank you for reminding me, Andrew. That's more of a sphere of objects rather than a belt of objects. I mean, we think of a belt as being within the plane of the solar system, and as indeed the asteroid belt is. The trans-Neptunian objects are much more highly inclined in their orbit, so they're not really a belt, but they're more like a belt than the Oort-cloud, which is thought to be something that surrounds the solar system completely, and is, yes, again, it's the outer edges of this blob of gas and dust from which the solar system formed. So the Oort-cloud is where the comets come from, and they are mostly made of ice. So that's the big difference.
Yeah, all right. So the answer to Sandy's question is yes-ish.
It's yes, and it's big time yes, really, because we've got, so much more that we now know about the solar system and its various families of minor objects, small objects, which are important to us because these things occasionally collide with the Earth. So that's why we need to know about them.
Would it be logical to suggest that these kinds of belts exist in other solar systems?
Yeah, I think so. There's the problem with trying to discover them is that the objects in them are so small that they're, trying to detect them from the distance that we are, which is measured in light years rather than millions of kilometres as we are in the solar system. That's a difficult task, but maybe one day we'll find some evidence. There is actually evidence. There's evidence of comet clouds, for example, around one star, Fomalhaut, if I remember rightly, had an object that was in its protoplanetary disk. That's the disk of stuff that's going to form planets that actually broke up into pieces, and it's thought to have been an asteroid collision. And we've also seen there's a very peculiar star that has a brightness range that changes, and the thinking is that we're seeing a cloud of comets passing in front of it. So yes, the evidence is there.
Right. Okay. Thank you, Sandy. Great question. And yes, you were right.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Our final question today comes from Steve.
Hi guys, it's Steve here from Liverpool in England. Actually just across the river from Liverpool, so technically a plastic scouser. Just a question reference, do you ever think a von Braun wheel or, wheel space station will ever be built? It's within our capabilities now, I think, with multiple launches, a modular design. They could even sell different modules to hotels, etc. But do you think it'll ever be built? Thank you. Take care and carry on with the show. Cheers. Bye.
Good on you, Steve. Thank you. I'll be visiting Liverpool sometime next year. Can't wait. Can't wait.
Got to go to the Beatles experience, Andrew. It's great.
That's exactly what I'm going to do. Yeah, I'm going to do the Beatles tour. Yeah. Space Wheel. The first time I ever became aware of a space wheel, Fred, was when I was a kid and I used to watch a TV show called Space Patrol. It was one of those marionette type shows. Captain Scarlet was probably the most famous of the shows. This one was called Space Patrol, and one of the spaceships was actually a space wheel. I don't remember much more about it than that. I do remember a strange space creature called Gabler, and they were trying to teach him to say medicine, but he kept saying pencil instead. I don't know why that's stuck in my head. Say pencil. No, say medicine, Gabler, he'd say pencil. Or was it say pencil, Gabler, he'd say medicine? It was some weird interstellar bird. I've got some strange memories from my childhood, but that one sticks out because of the space wheel. Do you think we'll ever build one?
I do, because it is the most direct way of trying to provide, well, it's the only way we know of trying to provide artificial gravity in a spacecraft that's away from the Earth. You've got to be very careful about it, though, because there are only certain limits between which you can build it in terms of diameter and how fast it rotates. What gives me some confidence in this is a conversation I had, it's quite a number of years ago now, but with the husband of Linda Spilker. Linda Spilker was the mission scientist for Cassini, for the Cassini space mission. Her husband, Tom, is a space engineer, contracted to NASA. He was at the time, I guess he probably still is. And his speciality is space wheels. It's sort of designing the possibility of these large rotating structures in space that will give you artificial gravity. When I think of the future of humankind, I tend to think of them not as colonizing Mars, which I think would be a bad thing to do, but I think of them building megastructures in space which might have artificial gravity, a bit like the Halo world from that very well-known early game.
Oh, yeah.
It was in the early years of the century.
Loved playing that game with the boys when they were at home, and of course they made it into a TV series, although that got canned after 2 seasons. But it's become a huge franchise. Did you know, I might have mentioned this before, but in Halo there was a Private Chips Dubbo, one of the characters. Yeah, Private Chips Dubbo, and he had an Australian accent. And
well, there you go.
So he appeared in the first version of the Halo video game, Private Chips Dubbo, because I'm from Dubbo. This is where I am. So, yeah. So somebody must, that's a great name. Love it. And he didn't get killed off. He wasn't, he wasn't a red shirt. Sorry, I'm digressing. Space wheels, yes. But you're right. The Halo was a space wheel.
A big one. Yeah. And if we could master the engineering to build something like that, I think that's a far better way than colonizing some other world that might have, rudimentary microscopic life on it.
So if you built a space wheel, and as you said, you've got to be careful because of size and speeds and creating that 1G effect, would bigger be better because you wouldn't have to rotate it nearly as fast, or I don't know.
Yeah. It's a fine line between the two. I looked at some of the work that Tom Spilker has done, and you want it big enough that it mimics gravity rather than making you feel sick, which is what happens with the smaller ones. And you want to ensure that if you drop something in this artificial gravity, it just goes directly downwards rather than moving sideways, which if it's too small and rotating too quickly, then it would do, or moving slightly sideways.
I'm just thinking all these questions as I go, but if you did build a space wheel in orbit around Earth as a hotel or whatever, a research centre, probably both in years to come, and who knows what else. But would you have it pointing at Earth on its axis or on its wheel? Because if you had it sort of wheel up, then you'd be standing with your feet in proximity to Earth. But if you put it on its axis, you'd actually be standing sideways.
Yes. I think what you might
do both, couldn't you?
Yeah, you could. I think you'd. I'm guessing here that what you'd want to do is really line it up in terms of where the sun is. So if you had it with its axis pointing towards the Earth, but in a geostationary orbit, so it was going around the Earth once a day, that would mean that you'd sort of mimic the 24-hour cycle of night and day. In a way that you wouldn't if it was some other way.
That's a good thought. Yeah, actually, that's a really good thought. Yeah, I trust you to come up with a better idea than me. Yeah, I'm glad you did. That makes perfect sense. So the answer is yes, probably it will happen. Why hasn't it happened yet? I think they've been focused on other things, Fred, I suppose.
It's fairly significant engineering, There was certainly talk of early in the idea of sending people to Mars, probably a couple of decades ago, of making 2 spacecraft that are tied together and rotate about their common centre of gravity. and that basically provides artificial gravity. But even that's turned out to be just a little bit beyond the engineering we've got at the moment.
Although we sound like we're going to get there. Thanks, Steve. Hope you're well. Hope all is well in Liverpool. And thanks for your questions. We've got a whole bunch of new questions that have come in that we're going to get through. That doesn't mean you should not send them to us. So go to our website, spacenutspodcast.com or spacenuts.io, and have a look around while you're there. But if you've got a device with a microphone, like a smartphone or a computer or whatever, you can send us audio questions. Just don't forget to tell us who you are and where you're from, or you can send us text questions via the AMA link on our homepage. And that's about it. Fred, thanks so much for answering all those questions for us today.
It's a pleasure. It's what I do, so I'm delighted to do that.
All right. And we'll catch up with you again real soon. Professor Fred Watson, astronomer at large, and Hugh in the studio, who I think he was taking the bins out when we started this episode. I don't think he's back.
I've got to do that as well. I have to take the bins. Thank you, Andrew. I've
got to do it tomorrow. And from me, Andrew Dunkley, thanks for your company. Catch you on the next episode of Space Nuts. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.